Alright, we have reached part 3 of our lecture where we're going to tackle this big problem about why does flow become detached. Now, flow can actually become detached as it flows over topography in two different ways. There can be, or orography, subtle differences in those two terms. The flow can either become detached on the windward side, the upwind side of the topography, or it can become detached on the lee side. And just for the purposes of brevity and clarity, let's go ahead and just focus on what goes on the lee side of the mountain as to why the flow becomes detached and so on. And again, we're going to be thinking about complicated terrain here, particularly, a nice steep mountain or something like that. And, but the same idea would apply to smaller obstacles to the flow, like this wing being pitched at a certain angle with respect to the flow. Clearly we have the flow separating on its lee side and so on. But what's going to end up deciding whether the flow is going to detach or not? And maybe it's not all that surprising that we're coming back to an idea that we had in the last lecture, and that is what's going to determine it at any given location where the slope is no longer an issue because the slope's not changing is the Froude number. Let me be more clear about that. If we've decided we're building a wind farm at this location, suddenly the slope of the terrain is not the issue anymore, right? Because we are no longer going to be changing that. Now it's about how the flow is adapting to the features that we are dealing with in fact. And the parameter that is going to be describing how the flow deals with that is going to be our new friend, the Froude number. And I provided you the equation for the Froude number over there. And you might remember that in Froude number in the numerator it had that u for the wind speed, and in the denominator it had that w, which was the width of the obstacle to the flow, the hill or the mountain or whatever. And it also had that NBV, which was the Brunt-Väisälä frequency. And we kind of hand-waved that away before and said that Brunt-Väisälä frequency was about stability, and I didn't give you a mathematical equation because I said it'll come back. Guess what? It came back. Alright, so let's take a look here. Now, I gave you 3 different mathematical definitions here of the Brunt-Väisälä frequency. The top 2 are mathematically exact, where they're talking about properties like the virtual temperature and the rate of change of virtual temperature with respect to height. In the middle one there, we've got things like rate of change of virtual potential temperature. And you're saying, Dr. Shrug, you have no idea what virtual temperature is. And I have no idea what virtual potential temperature is. And that's okay. Virtual potential temperature and virtual temperature are 2 terms that are an adjustment to the real temperature or the real potential temperature based on the humidity of the air, and to a good approximation, they're the same thing. That virtual temperature and temperature are basically the same thing. Or virtual potential temperature and potential temperature, they're basically the same. I mean, the atmospheric science professor in me has chest pains when I tell students that they're the same thing. They're not the same thing, but they're close enough for government work. Okay, we're fine with this here, which means I can make that substitution and okay, now I can't use exactly equals, I gotta use that wavy line equals in the 3rd equation there. But to a good approximation, the Brunt-Väisälä frequency is this relatively straightforward thing there that's got gravity and temperature and the rate of change of potential temperature with respect to height in it. Ah, okay. That rate of change of potential temperature with respect to height, partial theta, partial z, was something we really beat into your head in the previous module of the course. That's a measure of static stability. And since that's the main thing that's in here, no wonder NBV is a measure of static stability. Okay? I mean, change in potential temperature with respect to height, remember, if it was equal to 0, the atmosphere was statically neutral, and the bigger that number got, the more and more statically stable the atmosphere was. Okay, so basically I can see, I hate remembering all that stuff. I mean, I don't hate it, but I'm sure you do. But that makes sense. Okay, we've got a connection here. This NBV, this Brunt-Väisälä frequency, is really just very closely related to our measure of stability. Okay, I see that. So now let's say we're going to take this idea and we're going to apply it to the lee side of some mountains. And again, I'm going to keep that little bar at the top of the page there that says on the lee side of orographic features, because strictly speaking, these ideas only apply there. But we also only have so much time in our lives. Well, let's look at this Froude number And we'll give ourselves three possibilities here. What if the Froude number is very big, what if it's very small, and what if it's in between? So let's start with situations where the Froude number gets really big, far bigger than 1. And I look at my equation for the Froude number, and I can see that that means either u is very big, or which would be very strong winds, or Brunt by Solid frequency is very small, like gets down near 0, where it would be statically neutral. So we have a situation where some combination of the flow is very strong and or the flow is, the layer of the atmosphere is almost statically neutral. And what we're going to get when the flow flows over a mountain range like that is this wild possibility where the flow, as it goes over, sets up it separates and creates a detached flow feature known as a cavity. And this is going to be, have all the nifty features of like a separation bubble, like the flow at the surface is in the opposite direction of the overall flow. Cavities are, and in general, this whole flow feature will have much lower wind speeds than it would have been if it had stayed attached. Okay, all right, I mean, I can see where that could be something that could happen to the flow. What about the situation where the Froude number gets really, really small, much smaller than 1? Well then, apparently, again looking at my definition there of the Froude number, if that number is going to be really small, then apparently either u is really small, which means the flow is really weak, or the atmosphere is very stable. Okay, because that would make the denominator really big there. Okay, mathematically that makes some sense. Let's figure this thing out with a little diagram here. I see that my flow is staying attached to the mountain there. Now this diagram is not 3D or something like that, so you can't really see. Those lower two wind streamlines that I'm showing there are like going around the mountain. You can't really tell that because it's not 3D. A little bit of the flow is going over the mountain, but in the case of the mountain area, the vicinity of the mountain itself, by and large, the flow is following it. But we're going to be getting some kind of wave-looking features up near the top of the mountain there as well. These are called mountain waves. I better be able to explain what that's all about. So I've got my little magnifying glass tool thing out there again on this PowerPoint slide, and let's go take a look over here at the top of the mountain. So over there at the top of the mountain I have illustrated an air parcel, and I've labeled it there in blue, and that air parcel has been forced to do a little bit of rising as it goes over this orographic feature. Okay, I can get that. I mean, that's what attached flow means. At least some of the flow is going to go up and over. Alright. Now, my Froude number was small. That meant that the air was statically stable. Remember, that's part of what NBV had to be big, so it's statically stable. We know that's for sure. Alright, we just lifted an air parcel in an environment that is statically stable. Well, what does statically stable layer mean with regard to an air parcel we have moved? It means that it's now experiencing an acceleration downward. And so, like, if I take that air parcel and just, now we're done being over the mountain, the air parcel is now feeling an acceleration downward. Alright? It's going to get back to its original altitude, which I have highlighted there in that little blue line. At which point it's no longer experiencing any acceleration, but it is an object in motion that stays in motion per Newton's first law. It's going to continue moving downward and overshoot its original altitude, and continue going down until it reaches some new altitude, at which, well, now we have lowered an air parcel in an atmosphere that is statically stable. Statically stable resists all vertical motions. So lowering the air parcel, that means that that air parcel has now experiencing positive buoyancy. It has experiencing a restoring force, pushing it back towards the altitude from which it came. So now it's going to experience an upward acceleration. And we've set in motion kind of a wave motion here, right? The air parcel rises past its original altitude, experiences negative buoyancy, sinks, goes past its original altitude, gets down low. Now it is too warm for its environment. It experiences a positive acceleration upward, and we get this oscillation motion. And of course, because the flow is also happening, it's not just oscillating, it's moving along, and you get these wave motions. The result is a series of mountain waves on the lee side of the mountain. Okay, I like them. That looks really cool. We've set up these little motions or these little waves in the wind. Okay, we need some way to describe them. I want to be able to describe what those waves look like. Well, one possibility as to how we could do it would be to describe the period of those waves. As in, like, here's an air parcel. How many seconds does it take for it to go through one whole wave from one crest of one wave to the crest of the other? Period is a very logical way to describe a motion that is oscillating. Okay. Period of a pendulum, or any kind of motion, the period of a spring or something like that. Period is a useful way to do that. As it happens, period is not mathematically the nicest way to do such a thing like that. Period is actually related to the concept of frequency by this little equation right here. Period has units of seconds, so frequency actually works out to having units of per second. It's actually radians per second. Oh, wait a minute. So we could describe these waves using in terms of their period, or something called their frequency. I bet you see what's coming here. Yeah, that's what the Brunt-Väisälä frequency is. The Brunt-Väisälä frequency is the frequency of these waves that are created in this statically stable environment on the lee side of the mountains. So Brunt-Väisälä frequency kind of plays two roles. It's both the stability of the atmosphere, and it is a measure of the frequency of the waves that will be produced in that stable atmosphere. Isn't that cool? Now, period has units of like seconds, so if you think it through, frequency, including Brunt-Väisälä frequency, has units of like per second. So you can think of it as being like how many waves will happen per second. Well, it's obviously a tiny fraction of one, right? In practice, those waves, the period of those waves typically is on the order of minutes or hundreds of seconds. So, per second, they're a very small number, but okay, it's a measure of stability, and it's a measure of the frequency of those mountain waves. In fact, we can think about it. Now, I apologize for the ways in which this is not a perfectly attractive diagram here, but I tried to show you three different environments here, just kind of by manipulating the figure that I scanned, where we have mountain waves occurring in all three of these environments. They're all statically stable. If we didn't have a statically stable environment, you know what, if the environment was statically unstable, when the air parcel rose over the mountain, it would just keep rising. They wouldn't come back and make those oscillations. So these kind of mountain waves only happen when the atmosphere is statically stable. And what I have here is three situations where the top one is not so stable, and the bottom one is extremely stable. And what you see is, at the top one, where the stability is low, you end up with a low value of the Brunt-Väisälä frequency, and a high value to the period. So it takes a very long time for that air parcel to make its oscillation upward and downward back to the top of the next wave crest. Whereas like in the bottom figure, where I made the stability very great, now my air parcel oscillates up and down very quickly as the wind carries it off to the right side of the diagram there. The static stability is high. Feel free to work through and show that that means the Brunt-Väisälä frequency is high. And feel free to work through and show that that means that the period is short. These waves happen very fast. The air parcels oscillate up and downward relatively fast. Again, fast may be on the order of minutes or something like that. Oh, this is pretty slick. I love this thing about Brunt-Väisälä frequency. Now, when you create those mountain waves, an interesting thing can happen. Anytime you lift an air parcel, you can form clouds. It depends entirely on how far you lift it and how much water vapor there is in the air parcel, but it could happen. So, well, when I look at that oscillation, that mountain wave on the lee side of this mountain here, I'm seeing that half the time the air parcel is going up. So if there's enough water vapor to work with, that could mean that we get wave clouds, clouds on the downwind side of the mountain. I want to show you a really cool example of that. Here's a satellite picture showing winds blowing from like the bottom left corner of your screen towards the top right. And air is flowing over. You might even be able to pick it out there. There's a little mountainous island right down there in the bottom left corner of your screen. And see those mountain waves as you go forward? Each time you see those clouds, that's where the air parcel is going up. The clear area is where the air parcel is going down. The next part is where the next cloud is where the air is going up. Then the next clear part is where the air is going down, associated with how the mountain waves set up downstream from that mountainous island are creating clouds. Isn't that cool? I love that picture. These are by no means rare. I just happen to like that particular figure. Now, just for completeness, we have talked about a situation where the Froude number was very big, way bigger than 1. That's when we got that kind of flow that separated and made cavities and so on. Or we talked about situations where the fluid number was way less than 1, and we got those mountain waves, and we got flow that stayed detached, and so on. But what about if the fluid number is in that in-between range, near 1? Well, in that case, the Brunt-Väisälä frequency is associated with a wavelength that's actually pretty darn close to the width of a orographic feature. Okay, combines the U-wind and the Brunt-Väisälä frequency to get a wavelength that's almost exactly the same as the size of the mountain, and what you get is giant mountain waves. You get, the right word, the verb here is that the flow resonates with the terrain. And you don't get small, aren't they meteorologically curious waves. You get these enormous waves downstream. As the flow produces huge waves, inside of each of those waves you're going to produce rotors, or rotor circulations. And these can be incredibly hazardous to aircraft, with big shifts in the wind with respect to height and so on. You do not want to be trying to do flight operations if there's these kinds of resonating flow over a mountain range. Just because that word rotor is kind of interesting. Rotor, coming from the glossary of meteorology, it says that the circulation of flow is around a horizontal or nearly horizontal axis, and it's associated with the flow over a lee side of a barrier, such as a mountain range. Ooh, that's pretty cool. See how different kinds of flow, that's another example of a separated flow, detached flow, can happen under different regimes, under different ranges of the Froude number. Cool. Okay, we're at the end of this lecture here. Let me ask you 3 quick questions before you get ready to move on to the next lecture. Question 5. The Brunt-Väisälä frequency gets blank as the atmosphere goes from being statically stable to being even more statically stable. In other words, as the static stability increases. Is it getting bigger or smaller? And is it positive or negative? Those are your 4 options right there. Alright, make a choice from those 4 options and get some feedback before you move on to question 6 rather.